Hey, what's your name? Jared. Jared. So Jared, this is Jared's screen up there on the board, and so yes, you can see what he's doing. So if he were to press Control and arrow to the right, then he's going to go to the next page. And what's fun about this one, and Jared could do this, he could come over here and he could grab this little point right here. This is the point to move. You can do Control click. Control click will grab the point. You see the click in the middle of the touchpad has a hand, but that hand is closed. And so Control, since it's blue, Control click, and then you could move it. Hey, what happens as they go further away from each other? The gravitational force, does it get bigger or smaller? Smaller. It gets smaller. Hey, let's go from when they're at R and the force is said to be, actually if I can get to R, there you go, and then I'll give it to you so you can play. So when you're at R, then it's F. What happens if you double the R?
Oh, half of.
Ooh, move it to twice the R and see if it's half. It's 6.5. Okay, so he's going to move it to 2R, and he's getting closer, getting closer. Does that look like it's half of the force?
It's a square root.
It's a square. It's an inverse square law relationship. Yep. So it goes a little something like this. Newton's universal law of gravity. F equals G, M1, M2, all over R squared. Yes, it's true. Oh, gravity, we cannot feel you, guarantee. So it's an inverse square law relationship. Sometimes, like on your equation sheet, they put a negative there, and that negative simply means it's attractive. If you were to do E and M, then when you get a negative for Coulomb's law, then you're like, oh, that means it's an attractive force. If you got positive, then it would be repelling, and gravity is always attractive. And you guys actually enjoy calculus, and so do you know? Let's see here. If we had, how about the potential energy? So gravitational potential energy, on the front of that packet, you probably have some nice summary of some goodies. But G, what we got here? How about an M1, an M2, and it's actually divided by R for the potential energy, the gravitational potential energy. Maybe it even has a negative on it. I bet it does have a negative. And it's divided by R. Do you know what divided by R is the same thing as R to the negative 1? Would you not agree with that?
I would agree.
Yeah. And so here's something fun for AP Physics C. F, the force, is the negative derivative of the potential energy with respect to position, with respect to the R. Could you take the derivative of this?
Yeah.
Oh, but it's a okay. So at first you get a positive, right? You got G, M1, M2, and then power rule, R to the
negative 2.
R to the negative 2. Look, it's like R to the negative 2. And then because it's the negative derivative of the potential energy, then there's force. And it works for other things too. For example, you guys know spring, the spring potential energy? 1/2 kx squared.
Yeah.
So what's the negative derivative of the potential energy with respect to position? What's the derivative of that with respect to x? Kx, maybe even with the negative on it, right? Hey, what's negative kx? That's the force. Hooke's law. Remember Hooke's law?
So what's the value of Coulomb's constant? Like, what is, do you know the value of it?
Yeah, 8.99. Some people just go 9E9. 8.99 times instead of the 9. Compare that to the gravitational constant, which, yeah, these calculators know it as an underscore GC. The gravitational constant is a 6.67
times 10 to the negative 11.
Yep, which is really tiny. Negative 11, 10 to the negative 11, compared to Coulomb's constant, which is positive 9. It's huge compared to that one. So,
That was very useful.
getting ready for the E and M stuff.
What's Jacob did come that in?
Huh? I actually didn't find it in our book. I was, when you calculate state velocities, it helps.
If we were to move on to page 2.2, which you could control arrow to the right, control arrow to the right. Ooh, I'm going to ask you this question right here. When M1 and M2 are separated by a distance r, the force of attraction between them is F. If the distance r between the two masses was cut in half. If we cut the distance in half, what do you think the force is?
What page are we on?
This is just a
Oh, this
question
is
that
just
just
like a-
popped up on your screen.
Okay.
It is going to relate to one of the other multiple choice questions. And so actually I'll queue up that other multiple choice question while you guys see about answering this one. So legitimate question, where are we? We are gravity students, gravity, yes?
Are we gonna answer that question?
Yes, we will. I was just queuing up the one that's related to this one. At least I think I am. Oh, maybe? Maybe not. Found it. Yeah, let's do it. All right, so the one that you guys are thinking about, the one you guys are working on, the correct answer from how many of you? Is that everybody?
No.
Made a choice, 7 of you. I think we are getting closer to 7 people. We have more like 9. Sure, let's just call it good. Ooh, yeah, it's why is it 4F? Well, actually, if I
put numbers in and did the math.
he put numbers in, did the math. Nice, that's a good solution. If we back up to that previous page to 2.2, watch this. If we cut the distance in half, then there's an explanation for you. Because that 1/2 got squared. And a half squared is a fourth. And how many quarters go into a dollar? 4. So that's why it's 4F. Yeah. And so if you were to look, go to the very back of the packet and then go forward a few pages, you would find this question number 4. Question 4 says something very similar. 2 objects are separated by a distance r. If the gravitational force on the 2 is decreased to 1/3 of its original magnitude without changing the mass, then where is it located? What's the distance that time? So on your Inspire, you could, if you went to page 2.2, you could be playing with some various things and moving it around and seeing, I can get certain things, but actually you can't get the one that they're asking you about, which is nice. That you can't get that exact one. This is question number 4, and start it up.
I don't have answer choices.
It's coming. What's that?
What were they doing? I didn't have answer choices.
Okay. Yes. Okay. You've got a choice. Yeah, that's correct.
Is it?
It's fine. We'll find out. Let's give a few more people a moment.
I think it is.
I like how I see some people marking out. They're like, no, it can't be that because I know physics. So there's some of them you can like eliminate. Like you can either probably eliminate going this direction or going this direction because of something. We want it to be 1/3 of the original. So is it going to get closer together or
it's
further
not
apart? So we do need to
Further apart.
We do need them to be further apart.
Three people.
I think you could. Yeah. You could leave your quick poll. So quick poll was there's the quick poll. If you press the home or the on button and you go back to your current document, then you could be like, oh, I wanted to see that page 2.2 so I could play around with those little things. Here they are.
How do you get to 2.2?
Control arrow to the right or control arrow to the left.
Mine only has a 1.1.
Yeah, if you keep on
Keep on going.
going control arrow to the right, control to the right. If you control up arrow, then it looks like what's this guy called? Like a PowerPoint looking at all the little pages.
Mine to the right.
Then you can move down to 2.2. Okay. Stop presenter. All right, let's find out what the people are saying. We got 7 of you in, and the it'll show actually what the right answer is, so I will not reveal. Ooh, is it D or is it E? Let's do the math and see which one it is. Come here, math. Oh, dude, does that, doesn't it? Click. Oh, way too small. Be big. Please, thank you. And, okay. What's the math? The force, we know that we want the force to be a third of what it was originally. Originally we had a G, a certain mass, a certain other mass, and 1 and 2, over the R squared. So what do we have to put in there for R so that we would get 1/3?
3.
What 3 would be squared?
No, maybe nobody got it right.
If you did 3 squared, that would give you 9 over here. So if I had 3 squared, that would give you 9. Oh, that's not what I wanted. I didn't want 9. I wanted to have just 3. How do you get just 3? Square root of 3 squared gives you that. Yeah. And so that's why all these people who pick choice C, good job to student F and J and I. It's already marked right as it was. Yeah. So yes, C is correct. Again, looking at our a little file that I sent you, then it was page gravity. Yeah, there it is. So watch, if I move it out to square root of 2, then square root of 2 got squared. It was a half. I didn't have a 1/3 or square root of 3 spot. Yeah, 2, then that'd be a 4. If you move it out to 3, oh, that's 1/9. Yeah, that's not 3, 1/3 of the force. So there's that. Doop. Check. That's interesting. Do you guys know Kepler's laws? Kepler's laws of planetary motion. Planets orbit in what shape? Planets orbit in ellipses. Yep. Geometry trace. So planets orbit in ellipses. Hey, look, there's a nice little ellipse, isn't it? Oh, I can just play over here. And then the second law says that planets sweep out equal area, like this area over here is equal to like this area over here. Sweeps out equal area in equal time. The amount of time it takes to go from there to there is equal to the amount of time it takes to go from there to there. An implication of the second law is, where is it going faster?
Where it's closer.
When it's closer. Good answer. Yep. So that's Kepler's second law. Oh, these are written for you on one of those early pages. You know how these things can be treated as notes? Yeah, sure. Thanks. So at the beginning of this, you have lots of nice formulas and then notes. And yep, there's some formulas that we talked about there at the beginning. And there's Kepler's law in terms of the ratio of the third law. Oh, there they are, written right there at the bottom of the page. Who knows? Kepler's laws. First law, planets orbit in ellipses. Second law, equal area, equal time intervals. This line sweeps out equal area, equal time intervals. And the third one is a relationship between two different planets and the relationship of the orbital period, the ratio of the periods raised to the power of 2 is equal to the ratio of the distances, t's to the 2 and r's raised to the power of 3. That's Kepler's third law. So, knowing some of these Kepler's laws can be handy for being successful with the other multiple choice questions. Yeah, particularly this first question. So number 1. Question, there you go. Number 1, starter up. So based on that quick little thing about Kepler's laws, do you know which one is the correct answer for number 1? Three people made a choice. According to Kepler's third law, the ratio of the periods, ratio of power 2 is equal to the ratio of the r's. So, in other words, when it's further away, or when it's the smaller the orbital radius, the longer the period, or the larger the orbital radius, the shorter the period. The larger the orbital radius, the longer the period. Long means like big, big time, more time. Smaller orbital radius is oh, we got acceleration. Finally switched up into something different. And then the larger the orbital radius of the satellite, the bigger the gravitational force. This last one we kind of want to laugh at, don't we? When you go further away, there's more gravitational force. No. So, yeah.
That's so funny. My answer was the last one, but I was on the wrong question.
Oh, okay. Were you on number 2?
I was on,
Okay, don't tell them. Shh. Yeah, we don't want to give it away. Okay, yeah. So if you, for number 1, if you were picking an answer for number 1, the best answer is yay, the C's have it. Yep. If you are further away, it moves slower. Yep, makes sense. Kind of like the second law, when it's closer, it's going faster. Number 2 is a pretty straightforward one. Yeah, actually, let's do that. Let me explain something that's pretty helpful. On one of those first pages of this packet, you have some stuff, and you're like, where did that come from? And actually, how about the second one? Yeah, there it is. Determine the speed of a satellite in terms of the given quantities. As soon as somebody says something is going in a circle, in the world of physics, what do you guys want to think about when you think of if somebody says, hey, something's going in a circle?
Rotation.
I don't know if you said it or not, but what I would say would be centripetal. When somebody says circle, then I'm going to think centripetal. And what is supplying that centripetal force for something to go around in a circle? So we don't draw on a free body diagram. I'm not sure what this arrow is doing here, but that arrow pointing in towards the center of that one would be the force of gravity. We are about to derive, and maybe that's actually what it's asking us to do, determine the speed v of the satellite in terms of the given quantities. We're going to derive the, we're doing free response number 1, the orbital velocity. Or maybe, in fact, you can determine the orbital velocity. Call them the things they told you to call it, like the centripetal force. What do you think about for centripetal force? What is the formula for centripetal force? V squared over r is centripetal acceleration, and if you multiply it by the mass of the thing that's out there, then totally agree with that. Gravitational force. What's the gravitational force? G. And how about a capital M, because they said use a capital M? Divided by r squared. So, granted, if you want to get points for A, you need to put that down there underneath A. It's just I'm a little bit limited on space. You can't see if I write. Yeah, exactly. And so this stuff, if you want to get points for A, you need to put that stuff underneath A. If you put it somewhere else, then they don't necessarily grade somewhere else. Yeah. Important tips. So solve for V, and you're going to get all those points right, especially if you were to put it. Yeah, exactly. That's good. So it's got to go down there where it says A. Yeah,
that's hard to say.
Oh, is that what it was?
Yeah.
And now, I'm trying to know it here. Sometimes some verifications where you have to
I hear you saying, yeah.
Yeah.
So you speak English.
Right. Because you're like, that's my capital. Sometimes, especially when you have both of them. So good. Funny thing is that is written several pages, like the very first pages. Let's see here. You go down, then you get that, you get that. Oh, there it is. Oh, that's escape velocity. Hey, how does the escape velocity differ from what you guys just found for the orbital velocity? Where's the orbital velocity? There it is.
There's a 2.
There's a 2. What in the world, and why is there a 2? And actually, there's more things that are different than what you actually know about. we found out that for the orbital velocity, you just derived really nicely. Good job deriving orbital velocity. Click. Yes. But what about this escape velocity? What is different between the two of them? So there's more things that are different than what you actually are realizing. So for orbital velocity, you've got it right here. And so yes, good job figuring that out. What is that R? What is this? What is this R?
Radius of light.
Yeah, I know that you. Oh, I don't have to keep going over that. I know that you, like thinking about it in terms of, radius. But let's see.
Distance to the center of the.
Yes, there we're getting it. It's the distance between the center of the two objects. In fact, that's exactly what this thing says in the beginning. The force F depends on the distance between the center of the two masses. That R is the distance between the center of the two masses. Now, if you had massive sun and you had massive Earth, the reality is actually is not at the center of the sun. Well, we orbit in an ellipse, and it's a little bit offset from the center of the sun because we're going in an ellipse. But anyway, there's what your R is. Check. So let's do escape velocity. This might not be question B. Let's read what question B is and confirm that that is not what question B is.
Mechanical energy.
Yeah, see, that's something totally different. But this is valuable. I wouldn't necessarily put it in B. Here's an important aside. So you told me that R right there, if I had, like I say, a planet right here, and I had a satellite orbiting the planet, is that R the radius of the Earth? No. This lowercase r is actually, the radius of the Earth plus something, right? I don't know what you want to call it. Maybe the altitude, maybe you call it an h for the height, or you could call it the altitude, how far above the surface of the Earth it is. So the radius of the Earth plus, I'm calling altitude, I guess. And so that's one important thing to note, that the difference between this orbital velocity, that's what your r is. That's real. People mess up because they're like, the r is the radius of the Earth. Oh, no, it's not. Because most things don't orbit it at the surface. That'd be weird. I've pretended like I've done that before. Hey, I'm going to go out in the hallway, I'm going to throw this. Let's go find out how fast I had to throw it. So I send it into orbit around, and then I go out and catch it later on. It's like going so fast. It's right, crazy. So what about if you had a nice little Earth, and we had a little rocket here on the surface of the Earth, and we wanted to send that rocket up into space. In fact, we wanted to give it the escape velocity. We wanted to give it enough velocity so that it would, leave and I can't find ever again. It's over here. Okay. So how fast? What is that velocity? What is the escape velocity?
11.2 kilometers.
So, and what if it was on a different planet? So in other words, what's the general equation for it? And it's 6 kilometers. Makes me wonder if it is. So this concept was free body diagram, do our sum of the forces, and it's equal to, it's going in a circle, centripetal. That force of gravity was equal to our centripetal. That's what the concept was for the last one. What's a physics concept? What's a basic physics concept for something totally leaving the Earth's gravity? We're trying to find escape velocity. Or just tell me a big key physics concept. I will use some gravity stuff. True. But it's a law of conservation. Yeah, conservation of energy. Yes. Well done. Sorry I didn't bring extra candy to throw at you. Yes, good answer. So conservation of energy. Conservation of mechanical energy. When we say mechanical energy, what is the definition of mechanical energy? Definition of mechanical energy? Sorry. Definition. What is mechanical energy?
That's a good question. Jacob?
There's the answer. What is
Oh.
mechanical energy is?
Kinetic energy plus potential.
The sum of the potential plus the kinetic energy. So we're saying that mechanical energy is conserved, and so the energy it started out with here on the surface initially is going to be equal to the final kinetic energy, final potential. So we're saying final potential. Okay. So we're talking about this thing called escape velocity, and let's see how it comes out of this. What is the gravitational potential energy on the surface of the planet? Negative G, mass of the rocket, mass of the planet, divided by r squared, where in this case the r literally is the radius of the planet. So that's that. And then plus, and we're going to give it so much kinetic energy it's able to escape. So what is kinetic energy? 1/2 mv squared. And that's equal to, okay, if it was able to just get far enough away and escape the velocity of the Earth, then what would be the kinetic energy when it's at that furthest away point? What's that? Thank you. Yes. Why is kinetic energy there? 0? Because that velocity is 0. So the kinetic energy would be 0. I'll write 1/2 m0 squared is 0. And then plus, okay, ready for this? If we are totally escaping the gravitational force of the Earth, do you know how far away you need to be for this to oh, I wrote that wrong. Sorry, don't square that guy right there. There, that's better. And you get in the habit of squaring it because that's what the force of gravity is. But what's the gravitational potential energy? Not squared, right? We took the derivative of that earlier and we saw that that was true. So that's better. How far away does this need to be in order to be 0? Infinitely far away, which, you know, we live in a finite universe, so we really can't get infinitely far away. The bigger the r gets, then the smaller it gets. So escape velocity, what we mean by escape velocity is this is 0 also. So both of these things are 0 on this side. Can you solve for v? And the answer is yes, you can, because you did. I saw you do that earlier. So you have this plus this is equal to 0, and if you solve for it, then maybe you already saw what the answer was for the escape velocity. The escape velocity is equal to, hey, negative comes over there, becomes positive. The lowercase m, does the mass of the satellite depend upon it? Nope, not for the orbital or for the escape velocity. Boom, there it is. This case, the r really is the radius of the Earth or whatever it's sitting on. You run that to the radius of that planet. And so there you go. That was handy stuff for you. The next question, I'll leave that up there for a moment more while you continue finishing thinking about that one. Should we do some of the hard stuff? Yeah, because they sometimes, and this is really actually would help you out for your physics, E&M, your electricity magnetism, they do this to you quite a bit when you do the E&M. You're like, whoa, what are you doing to me? They use, oh, okay, so this one's not as ridiculous as the one I was thinking about later on. Yeah, and we can do these actually in an easier way. Let's go with doing them in the easier way. Number 3, here's a hint, because it'd be nice if you could actually get it right. Number 3, let me cue it up so that it's ready to go to you. Here it goes, there's 1, there's 2, here comes 3. So 3 looks kind of weird. What do you know about density? It's actually, is that one on your equation sheet? It's on the physics 1 equation sheet. I don't think density is on our equation sheet. Yeah, it's mass per volume. It definitely is mass per volume.
D equals 1. D equals 1.
So we do know things like density is mass per capital V volume. And we do know the force, so you could totally write some equations for force. But if you're wanting to equate some things, like for example, if I were to write things like the acceleration, right? F is equal to, what's Newton's second law? F is equal to what? ma. So I'm going to write ma. And then over here I'll write g m1 into, or maybe I'll do a lowercase m and a capital M all over r squared. Yes, it's true. And so that lowercase m could cancel out. This a actually, or sometimes people call it g, but I guess we should call a, because right here it's called a1 and a2. But that's actually referred to, this a is called the gravitational field. This a, see it said ma, but I just canceled out that m over r squared. This is the gravitational field, or the acceleration of gravity, grav field. Sometimes they call it gravitation. So anyway, hey, do these two planets have the same mass? No. Do they have the same radius? No. Do they have the same acceleration? No. Do they have the same universal gravitational constant? Okay. So there's your hint. And if you like, hey, here's this equation, the g is going to be the same for both of them. So then maybe you could actually get it. So give it a try. And I think they hit start. Yeah. Number 3. That's
Not just a lowercase p, it's a Greek letter rho. Because otherwise it reminds you of momentum. You're like, yeah, momentum definition is this. I didn't know what it was. But that's a whole
It's a Greek letter rho. It's actually, this is how it's written on the physics 1 equation sheet, which is part of why I wrote it here for you. But yeah, essentially it just says density is mass per volume. I use a capital
We haven't
D.
done that yet, and in chemistry, they do D.
Capital D or something, maybe, or just lowercase d? D, oh, which is fairly awkward in terms of like, hey, distance. No. Distance is because there's mass for velocity. You know.
We needed a longer alphabet.
Yeah, real.
No, no.
Well, you think so?
Yeah, we just used other stuff.
Put in all the little 1s and 2s and it's got a choice of anything.
Absolutely not.
That's my head, but you know.
Yes. So put in right next to
This is Jacob's
equations.
But with, you know, 1s and 2s, or something that's two to become 1.
Like, I don't know.
And then, instead of mass, then we call it density times volume. And then,
Anybody know the volume of a sphere? And no, you don't have to know the volume of a sphere. You just have to. You just need to know. It depends upon the radius cubed. The volume would be radius cubed. Yeah, yeah. That'd be the other thing to get it right. Sometimes we can do some guessing. No. I mean, in the sense of, you know, sometimes things, you're like, no, it's not going to be one of these. Maybe you could. Seems hard. So keep going. Try it. You can do it. A1 equals G. Don't think I want to call it M. I think I want to call it like rho times volume. Rho 1 times the volume. Volume of a sphere is 4/3 pi r cubed. Ooh, for R1 I can call it R1 cubed. Divided by my R1 got squared. So
yeah.
all I did was I just said mass is density times the volume. And so do that for number 2, and then set the two g's equal to each other, and you can get it right.
On test when?
Too much for 4 hours of physics. Just keep doing it for you.
Where?
Yeah. So yeah, if you're curious of why this is why a certain right answer is, oh, and 2 people make a choice. Thanks for making a choice. Yeah. Appreciate you. The other one we would call A2, the acceleration number 2, is G density number 2 times the volume of the second one. What is the volume of the second one? 4/3 pi R2 gets squared cubed. And then in the denominator you have an R2 got squared. And so you're like, whoa, mess of stuff. Just a bunch of. So if you solve one of these for G and substitute it in for the other one, then you would see the right answer. Solve one of these for G, and the 4/3 and the pi go away. Oh, one other thing you want to do is say that R2 is equal to 2 R1s. Because none of these have any R's in it, and that's the reason why. Oh, we had 6 people make a choice.
4 squared, which is 2, which is whoa.
Why is it that the correct answer, did anybody get it? Let's see. Why is it that the correct answer is brought to us by this one person? By these couple people. So why is that? Well, because so actually I don't have to do the 4/3. They're going to cancel out here in just a minute. Yeah. All right. So
I'll do 2.
if you solve this for G, so G is equal to A1 on top, and then all this stuff's on the bottom. There's also be an R1 squared. It's an A1, R1 squared on top, and all these goodies in the denominator. Rho 1, 4/3 pi R1 cubed, and then if you put that in there to this G, or you could have done the other way around, because it'd be fun if it said A1 was equal to things. But anyway, if you put that in there, then you get lots of nice things canceling, as in, need more space. Yeah, go smartboard. And so now we can scroll down. Yeah, maybe it's not worth our time to keep on going, but we're so close. We're so close. Put it in there. This currently says A2 is equal to A1. So I'm putting in there everything that G is. You're going all in there. Go R1 squared. Keep going. Over rho 1, 4/3 pi R1 cubed. That's substituting the G in there. And I have a rho 2 on top. I have a 4/3 up there, pi. Hey, what's R2? Isn't R2 twice the R1s? Is that twice the R1? Yep. And then in the denominator, we're going to have twice the R1s and get squared. 4/3 pi, 4/3 pi. Let's see. Hey, how many R's do we have? We have R squared and we have R cubed. Hey, in the bottom we have R1 cubed. And so the R's are all going to go away. Bye-bye R's. But you do have 2 gets cubed, which is 8. And then you have 2 got squared, which is 4. Yeah, but we're supposed to solve for the A1. If you solve for A1, then that 2 comes down to the denominator. Comes over here. Denominator. What's the correct answer be?
Yes.
Yep. There. That's the reason why.
Nice.
All right.
You did all that work on your work?
No, I just did it myself.
Yeah. He's like 4/3. We don't need to write all those 4/3. We know we're going to cancel that. All right. So that was
There's no way.
I know, right? So 5, 6, and 7. Could you queue up this number 5 because, and just leave it there because it's the same for number 6 and 7. So here comes number 5. Yeah, this one is literally a quick one. You can do it on your mark, get set, and read those options. It moves from A to E. Going from A to E, what happens to things? Does the kinetic energy stay the same, get bigger, get smaller?
Or increase.
Get smaller, get bigger.
Bigger is increase.
And then what happens to the angular momentum?
Constant.
Is he getting his team to all pick their one? So what do we know about what do we know about angular momentum?
It stays constant.
It's conserved. Angular momentum is conserved. What do you know about the speed? If it goes from A to E, what happens to the speed?
It's faster.
It goes faster as you get closer to the plane. It gets faster, which is the reason why the correct answer is boom. E. Ooh, 100%. Sweet.
I just had that question when I did.
Yes. That's a nice one.
I hope not.
How about number 6? So what concepts are going to be able to, so at point A is at its furthest point away, is 8, it tells you that it's 8r, and when it's the closest it is and it's r, the ratio of the planet's speed. Yeah, do we have any nice equation that has something about speed, the ratio of the planet's speed when it's there compared to when it's at this other spot? I wonder what kind of relationship we got. And so what am I doing? I'm doing number 6. Giddy up. 6, go. So why is it what it is? Number 6, number 6, number 6. So there's some fancy stuff you could do, but I would just think about conservation of angular momentum. Yep, good. And let's see, unfreeze. How many people are finished? We got our 7. Which we often have been getting 7 lately. And unfreeze. Just one person got it right. Yes. So why
Good
is
on
it,
me.
why is it 1/8 conservation of angular momentum? The MVR and so V1 and R1, and that's going to be equal to MVR at the other spots, and 2 and 2. So. How does the R at the one location compare to the R at the other location? So yeah, we're wanting the ratio of the planet's speed. But when it was, I could call A's and B's. So let's call it A was point A when it was 8R1. Yes. So VA and then 8R is equal to by masses is equal to the V at the E, and this would be just R. And your goal is to find the ratio of VA to VE, and the ratio of that one to that one would be? Yep. Conservation of angular momentum comes in handy for this one, for that last one. about the angular velocity, the planet's angular velocity at point A? They called it, they said it's omega sub A. The planet's angular velocity at point E. What do we think about when we think about angular velocity? Again, conservation of angular momentum. If you were thinking about conservation of angular momentum, my biggest question is, do you know anything about this I? All right, well, let you think about it and make a choice here for number 7. But I'll go ahead and keep on saying, same thing as before, conservation of angular momentum. The L is equal to the L. Or maybe we could say the L at location A is equal to the L at location E. And that would be an I times an omega. Hey, which one has a bigger I when it's at location A or location E? So what is that I anyway?
BT over R. Right?
That's W.
That's the W.
That's W.
Yes, that's what he was saying. BT over R. Still not quite following where that one came from.
Yep. Just,
Yeah, and so the I, and I think you do have something like on your equation sheet. Do you have like a
Excuse me, teachers and students. Students, please turn in your packet to your school table. Make sure your name is on each packet if you have more than one.
whole packet?
Also, we would like to announce the last winners of our gift card. Come to the library table to receive it. Jasmine Ormbrister, Luke Taylor, Jonathan Beasley, Jamie Ellenbach, Haley Kenton, Anna Izagira, E-Rose Baraha, Jackie Crosby, Brittany Bauman, Gavin Avery, Melanie Turkey, Dakira Wilton, Carson Stockwell, Kyle Thompson, and Leslie Lively.
I think they said my name wrong. They said Luke Taylor.
Because it's squared, the correct answer is actually E. Because that 8 got squared. Yeah. That's what I got. Yeah, E. So thanks for coming, and glad you guys were here. Since drove all the way over here, it was nice for people to actually be here.
Have you ever done that where they didn't really show up?
Yeah, E&M. I had a really small.